Let me show you how to be a good Bayesian. Change your predictions after taking information in.
When do you think this kind of new algorithm would be interesting to use instead of the classic HMC? Like, in which cases would you say people should give that a try instead of using the classic robust HMC method we have right now?
I think right now, so on paper, the algorithm we propose is really, really powerful because it will allow you to jump throughout your space and so to decorrelate your MCMC configurations extremely fast.
Yeah.
However, for this to happen, you have that the proposal that is made by your deep generative model as a new location, a new configuration in your MCMC chain is accepted.
Yeah.
So in the end, you don't have anymore the fact that you are jumping locally and that your decorrelation comes from the fact that you are going to make lots of local jumps. Here you could decorrelate in one step, but you need to accept. So the acceptance will be really what you need to care about in running the algorithm. And what is going to determine whether or not your acceptance is high is actually the agreement between your deep generative model and the target distribution you're after. And we have traditional challenges here in making the deep generative model look like exactly the target we want. There are issues with scalability and there are issues with, I would say, constraints. So you give me, let's say you are interested in Bayesian inference. So another case where we can apply this kind of algorithms, right? Because you have a posterior and you just want to sample from your posterior to make sense of it. Well, you give me a posterior distribution. It's in dimension 10, 100. I tell you, I know how to train normalizing flows, which are the specific type of generative models we are using here, in 10 or 100 dimension. So if you believe that your posterior is multimodal, that it will be hard for traditional algorithms to visit the entire landscape and equilibrate because there are some low density regions in between high density regions, go for it. If you actually are an astronomer and you want to marginalize over your initial conditions on a grid that represents the universe, and actually the posterior distribution you're interested in is variables that are in millions of dimension, we are not going to do it with you, and you should actually use something that is more general, something that will use a local search that is actually going to, be imperfect, right? Because it's going to be very, very hard also for this algorithm to work. But the magic of the machine learning will not scale yet to this type of dimensions.
Yeah, I see. And is that an avenue you're actively researching to basically how to scale these algorithms better to bigger scales?
Yeah, of course. Of course, we can always try to do better. As far as I'm concerned, I'm also very interested in sampling physical systems. And in physical systems, there are a lot of, prior information that you have on the system. You have symmetries, you have physical rules that you know that the system has to fulfill. Or maybe, multi-scale property of the probability distribution. You know that there are some self-similarity. You have information you can try to exploit in two ways, either in the sampling part, so how you're having this coupled MCMC with the deep generative models. So either in the way you make proposals, you can try to symmetrize them. You can try to, exploit the symmetry by any means, or you can also directly put it in the generative model. So those are things that really are crucial, and we understand very well nowadays that it's naive to think you will learn it all. You should really use as much information on your system as you may and as you can. After that, you can go one step further with machine learning. But in non-trivial systems, it would be deceiving to believe that you could just learn things.
Yeah. I mean, completely resonate with that. It's definitely something we will always tell students or clients, like, don't just, throw everything at the model that you can and just try to pray that the model works like that. But actually, you should probably use a generative perspective to try and find out what the best way of thinking about the problem is, what would be the good enough, simple enough model that you can come up with, and then try to run that. Yeah, so definitely I think that resonates with a lot of the audience, where think generatively. And from what I understand from what you said is also try to put as much knowledge and information as you have in your generative model. And then the deep neural network is here. The normalizing flow is here to help, but it's not going to be a magical solution to a suboptimally specified model.
Yes. I mean, of course, in all those problems, what's hidden behind is the curse of dimensionality, right? So if we are trying to learn something in very high dimension, and it could be arbitrarily hard. It could be that you cannot learn something in high dimension just because you would need to observe all the location in this high dimension to get the information. So of course, this is in general not the case because what we are trying to learn has some structure, some underlying structure that is actually described by fewer dimensions, and you actually need fewer observations to actually learn it. But the question is, how do you find those structures and how do you put them in? And this is where, therefore, we need to take into account as much as the knowledge we have on the system to make this learning as efficient as possible.
That's super interesting. And that's your paper, Adaptive Monte Carlo Augmented with Normalizing Flows, right?
So this is the paper where we did this generally, and I don't have yet a paper out where we are trying to really put the structure in the generative models, but that's the direction I'm actively researching.
Okay, yeah. I mean, so for sure, we'll put that paper. I just cited in the show notes for people who want to dig deeper. And also, if by the time this episode is out, you have the paper or a preprint, feel free to add that to the show notes or just tell me and I'll add that to the show notes. Because that sounds really interesting for people to read. So I'm curious, this idea of normalizing flows and running that deep neural network to help MCMC sample faster, converge faster to the TP concept. What was the main objective of doing that? I'm curious, why did you even start thinking and working on that?
Yes, I think for me, the answer is really this question of multimodality. So, the fact that you may be interested in priority distribution for which it's very hard to connect the different interesting regions. In statistical mechanics, it's something that we call actually metastability. So I don't know if it's a word you've already heard, but where some communities talk about multimodality, we talk about metastability. And metastability are at the heart of many interesting phenomena in physics, be it phase transitions. And therefore, it's something very challenging in the computations, but in the same time, very crucial that we have an understanding of. So, for us, it felt like there was this big opportunity with those probabilistic models that were so malleable, that were so, of course, hard to train, but then they give you so much. They give you an exact value for the densities that they encode, plus the possibility of sampling from them very easily, getting just a bunch of high AD samples just, in one run through a neural network. So for us, there was really this opportunity of studying multimodal distribution, in particular metastable systems from statistical mechanics with those tools.
Let me show you how to be a good Bayesian. Change your predictions after taking information in.